So this is going to be my solution to the 2019 AP Calculus BC free response question number 2. And it says, let S be the region bounded by the graph of the polar curve for theta from 0 to the square root of pi as shown in the figure above. And part A says to find the area of S. So you should simply know the formula for that. The area for a polar curve is 1/2 the integral of r squared d theta. First, let's go to our calculator and define this polar function. Define our, let's use x here. X equals 3 square root x times the sine of x squared. So the area for this, for the polar curve, is going to be 1/2 times the integral from 0 to the square root of pi. It already gives you the bounds of r of theta squared d theta. And this equals 1/2 integral from 0 to square root pi of r of x squared dx, which is equal to 3.534. That changes for part A. Part B says, what is the average distance from the origin to a point on the polar curve, r of theta? So you need to really understand the definition of what a polar curve is. And a polar curve is that distance from the polar curve to the origin. So you're essentially just finding the average value of the polar function over that interval. You should also have that formula memorized. That would be 1 over the square root of pi minus 0 times the integral from 0 to square root of pi of r of theta d theta. The average is just 1 over the interval times the integral over that interval. And this comes out to be 1 divided by the square root of pi times the integral from 0 to square root of pi of r of x dx. That is 1.580. Yeah, 1.580. I'm going to change for part B. Part C says there is a line through the origin with positive slope m that divides the region S into 2 regions with equal areas. Write but do not solve an equation involving one or more integrals whose solution gives the value of m. So you really have to remember your unit circle here, right? We're going to draw a bad unit circle, right? So if I have some angle theta with the origin, and this is the x coordinate, and that is the y coordinate, just by using some, we'll more explicitly label that actually. So this distance is y, and this distance is x. That's better. So the tangent of that angle is y over x. But this is also equal to the slope, right? Because y over x is equal to delta y over delta x, because that's just y final minus y initial over x final minus x initial, and x initial is just the origin. So delta y is equal to y, and delta x is equal to x. So therefore, theta is the inverse tangent of that slope. So at this point, part C, you need to write out the integral from 0 to that theta that divides it in half, which is the arctangent of m. So 1/2 integral from 0 to arctangent of m of r of theta squared d theta is equal to 1/2 of the entire area. So 1/2 using this expression here, this expression over here. 1/2 of this is 1/4, right? Or 1/2 times 1/2 is 1/4, so it'll be 1/4 times the integral from 0 to square root. It's a bad square root of pi of r squared, or r of theta. R of theta squared d theta. You could really write this expression a lot of different ways. This is the way that I like to write it. You could write this as the integral from 0 to the inverse tangent of m equals the integral from the inverse tangent of m to square root of pi. You can write this as this actual numerical value because you calculated the numerical value here, so you just divide this by 2, get around 1.75-ish. Really can't do that mental math in my head accurately. But yeah, that's the answer for part D. You could really write that out different ways, but I think the main focus here was recognizing that the slope of that line is the inverse tangent of that angle and plugging that final angle into the bound. Part D says, for k is greater than 0, let a of k be the area of the portion of region S that is also inside the circle, r equals k cosine theta. Find the limit as k approaches infinity of a of k. So this is a very conceptual question here. So we're gonna, we're kind of stuck here with the drawing, so I'm gonna draw this in a different color. So if I have let's say k is equal to 1, right? This is going to be this graph right here, right? A actual circle, not a badly drawn circle. And as k approaches infinity, let's say k is 5, the graph is going to look more like that. And as k gets bigger and bigger and bigger, this circle becomes infinite, right? So it's infinitely large circle. And when it's infinitely large, all of the area to the right of the x-axis is going to be bounded by the circle. So, and there's no area in region S that's below the x-axis. So this is all of the area in quadrant 1 of S. So it's simply the area from 0 to pi over 2. So limit as k approaches infinity of a of k is equal to 1/2 integral of 0 pi over 2 of r of theta squared d theta, which is equal to 0.5 integral 0 pi over 2 r of x squared dx, which is 3.324. The problem that I see with part D is that I really couldn't find a way to mathematically justify that. You can justify it with words saying as k approaches infinity, this circle becomes infinitely large, encompassing all area to the right of the y-axis, and the only area overlapping region S and all the area to the y-axis is region S from 0 to pi over 2. And that is my solution to question number 2.